Sample and hold circuits are a circuit that that keeps up with the voltage on the input, but can freeze that voltage at a given value wherever it was for a little while, so that you can do something with that voltage, like digitize it, or measure that voltage digitally with something. So you often see sample and hold circuits employed in ADCs, analog to digital converters. And so we begin by considering a set of two buffers, voltage followers here made out of op amps, and in between we have an RC circuit. And the idea is that the input voltage VC and Vout are all the same as long as Vin isn't varying too fast, greater than faster than the 1 over the RC time constant of the inner part. And that's basically just saying that VC has time enough to respond so that the voltage across the capacitor is charged up fully with Vin. Now, if we replace the resistor here with a FET, which in the ohmic regime is basically a variable resistor, then we have the same system. We have a resistor here, but the current can flow. We still charge up the capacitor, but we can quickly turn off the FET by changing the voltage on the gate and send it to be very cut off, in which case the charge on the capacitor just sits there. There's basically a very high resistance going this way. That's an open switch. There's a very high resistance this way because an ideal op amp has an infinite resistance between here. In real life, there's probably mega ohms of resistance in both cases, but it's still pretty big. So Vin there is still working. This op amp is still being fed back. The voltage here is changing along with Vin, but that doesn't get through, and VC can't go anywhere, so that Vout is whatever the frozen value at VC is. Another way we can make this circuit is to replace the first op amp with an OTA. So in this case, rather than having a feedback just locally with what was an op amp, we feed back the output voltage into there, so that a current flows here if Vout is different than Vin, as long as there's a gain coming through here. And so if Vout is bigger than Vin, then the current comes this way and discharges the capacitor until Vout equals Vin, in which case it stops. If Vout is lower than Vin, then a current will flow this way, charging up the capacitor until Vout is the same as Vin. So it works the same as before, but if we turn off the op amp by making IABC 0, then the gain of this is 0, and we have a very large input resistance here, but actually that's going to work as the resistance path backwards for the capacitor, and again we have a charge there that has nowhere to go, and we have time to do something with it here. So we've isolated this circuit. So both of these ways, the 2 op amp solution and the op amp in the 3080 OTA solution, you can use in Lab 22. I will note that one can also replace the second op amp with an enhancement mode MOSFET, as I've shown here, and I've also put in some reasonable resistors. So in this case, this is basically, you'll remember the emitter follower of the BJT. Well, this is a source follower circuit, so that we know that Vout is going to be close to the gate voltage here, and it's going to follow it, and in fact the feedback will make sure that Vout is the same as Vin. And again, so this works like the buffer we had before, but because it's a MOSFET, it has a very high input resistance, and so once we turn off the OTA, again, the capacitor is isolated. That wouldn't work with an emitter follower with the BJT here, because there's not nearly as large an input resistance, so this charge could leak off going down to the power source here.